Hello everybody, how's it going? Nice to see you all, and thanks for turning up. Yeah, this is not the first time I've been to JFocus. It's always a pleasure to visit Stockholm. 1 year, hopefully you may be able to convince Matthias to not do it in January, but like in the summertime where it's nice and warm. But apart from that, I have no complaints. So I run and co-founded a company called Opsian, which is a continuous profiling company. But this is not really a product talk directly as such. It's more about the methodology, the approach, and how you can understand what your production systems are doing better in general and at a technical level as well. So I'm going to be talking about a few different topics today. Firstly, I'm going to be talking about why performance tools matter and how they fit into your general kind of understanding, your big picture around understanding performance. Then I'm going to talk about the difference between your development and your production environment and why those two things can't be reasoned about in the same day, in the same time, in the same way. And then I'm going to talk about different ways you can measure those kind of production systems using things like monitoring logs, and also specifically a lot about profiling and how that can be done in a really low overhead way and accurate way. So when you think about problems that you can encounter in terms of your system, I mean, I'm thinking about performance problems here, but this applies to all sorts of things when you're writing software. There are three types of problems that you can kind of hit. And the first one, and the easiest type of thing, is the known, right? You know in any kind of current day system that accessing data in memory is going to be faster than on disk, okay? These are things that you can reason about a priori ahead of time when you're architecting your system, when you're designing things. And they're not necessarily things which you might want to validate when you look at your production system. Is this thing I thought was true, really true? But you really should know what's going on there. Then there's the known unknowns. So these are problems that you think before you've deployed a line of code to the real world. You know they might be a problem. You know there's something you might want to think about, but you don't know the exact details or how to solve that problem. So, for example, you might decide in your system that you want to have an in-memory cache, but you don't know how big that cache should grow. You don't necessarily know ahead of time what the different hardware is that your system is going to be deployed on. You don't know what, for example, the ratio of speed between your kind of CPU and disk access is. So you know that there might be things that you need to adjust or tune, but you don't know exactly the details ahead of time. And then there's the unknown unknowns. These are the kind of things that really cause you problems, the real head scratchers, the things that you didn't think about ahead of time, and you didn't even think that they could be a problem ahead of time. Like, for example, you write some beautiful, well-thought-through parallel algorithm in your code, and it turns out that actually the contention in your system is all on your logging library, right? That kind of problem that you wouldn't have thought about without looking at a real production system, without seeing what was going on there. And I think that's really where, and the context in which understanding a production system should be really thought of. It's not about knowing things that we can think about ahead of time. It's about having a hypothesis-free investigation, being more scientific, thinking about the unknown unknowns. And that's where we start thinking about how can we apply those theories in terms of our software that we write. Now, when you're writing functional tests for your code, so who here writes some kind of unit tests? Who here writes some kind of integration tests? Who writes some kind of end-to-end system tests? It's the same people every time, isn't it? Anyway, when you write those tests, you want to be able to run them on your development environment, your laptop, your desktop, whatever you're writing code on. And that makes sense, right? It's the easiest, the fastest way that you get your feedback loop, the fastest way that you can turn things around. But when you're investigating performance problems, there's a variety of reasons that we'll look at now. That development environment is not the best place to understand those performance problems. It's not the best place to test, evaluate, and measure what your software is actually doing. And the first reason, the first distinction between development environment and production system might be unrepresentative hardware that you have in your development system. So I develop a lot of code on my laptop. I sometimes work on a desktop at home. These things look very, very different from production systems that I deploy software to. Who here has the exact same hardware on their workstation, CPU, chip, memory, disk, everything as their production systems work on? Who here even deploys software to a homogeneous production hardware environment? Some people, probably some people. But anyway, most people have a very, very, very unrepresentative environment. And it's become more unrepresentative nowadays with advancements in terms of the way we deploy software. So who here deploys some software into a cloud-based system, right? Yeah, a lot of people. So it used to be, back in the day, that you would write some code on maybe a small, lightweight machine, and then you deploy it to some kind of bigger, more powerful server. And you could think to yourself that if things worked, if they met their performance objectives on your laptop, that it was solid for your bigger server. Now, that's not actually true in and of itself, because often you get situations which become bottlenecks on bigger servers, like lock contention issues that can only really be an issue as you hit to a higher number of cores, like 16 or 64 cores, that you wouldn't see so easily on a small 2-core laptop. But it's even less the case nowadays that we deploy to smaller VM instances in the cloud, in which you often find that those systems are frequently less powerful than the workstation that you write your software on. Then there's unrepresentative software. So this is a timeline of all the different Linux distros here. So who deploys software onto Linux in the room? And who are those people who uses Linux on their development environment? Some people. Who uses a Mac? Who uses Windows? Excellent. Brave Windows users holding their hands up there. Thank you. Thank you very much. But you find that if you use different operating systems like that, you can get very, very different behaviors in terms of the network stack, in terms of the way scheduling software works, often very, very different behaviors between different variations of the same software. So as part of the Spectre and Meltdown mitigations, regular security patches have often had huge impact in terms of the way the performance of your system works. There was a Windows update in, I think it was March of, 2016 now, where they tanked UDP throughput by 40% in a security patch, which was just all down to a Spectre and Meltdown mitigation. The version matters, the VM matters, all sorts of things like that matter. And if you get different versions in development and production, you can get different results. And then there's the biggest thing, the unrepresentative workloads. If you want to take a production performance problem and understand that and solve that problem in a development environment, you need to have something that's a performance test or a workload that's stressing the system in the same way that the real production system is doing, okay? Now, you might know, for example, what different endpoints on your system are being hit that's causing a performance bottleneck. But you don't necessarily know how that workload impacts, whether it's a steady state that you hit this performance problem at, whether it's a situation where you can match that level of throughput, but you can't match that level of throughput when you've just ramped up to that level of throughput after, say, deploying a new piece of software. That's something people hit. You don't necessarily know what the distribution between different read and write operations on your production system is that's causing that workload. And if you get a workload that's wrong or different from your production system, you can very, very easily waste time trying to fix the wrong problem, which is bad because it's a waste of your time, and it's also not so good for your customers, for your business that still has that problem going on in the real world. So workloads, performance testing is really hard to get right, a really challenging discipline, and often can be the result of misdiagnosed performance problems. Then there's the case that the JVM can sometimes have different behavior in different production environments and in different setups. Hotspot itself does adaptive optimization. Algorithms that you use depend upon the class of hardware that it detects you're running on. Instruction sets matter. There's also things like whether you've warmed up different systems. I once did some work on a clustering system, and we had nice, hot, well-optimized code, and we had like a kind of a strong leader, so a leader and a bunch of followers in a cluster. And the leader was going ahead and performing a lot of business logic. And when you had a failover and a new follower was elected to a leader after a net split or something like that, that would then be the primary runner of the business logic. And the problem with that kind of setup is that when you do adaptive optimization with hotspot, it spots that you're never really running that common code of your business logic on those follower nodes, and we would get big throughput reductions when you immediately flipped over from a leader to a follower because of that adaptive optimization. So production may well optimize differently depending upon those behaviors compared to your development environment. So sometimes you just have to say, I've no idea what I'm doing, I need to go and do some measurement. The dog looks cool, but you don't want to be that dog. And I don't mean that in the sense you don't know what you're doing with your life, I just mean that in the sense of your production system is a very different beast, and that's what you want to measure. So what are the different ways that we can go and measure and inspect our production software? Well, the first thing that we look at, or developers often look at, is system metrics, passive metrics, ambient metrics, or just metrics, whatever you want to call them, really. So these are pre-configured numerical measures that you can get out of lots of different types of software. Grafana and Prometheus are, I would say, the most popular things that people seem to be adopting at the moment in terms of open source solutions for gathering those kind of metrics. And they'll tell you things like, what is your CPU time usage at a certain point of time? You can look at things like, what are your page load times and response times? Metrics are really cheap, so when I say cheap here, I mean computationally cheap. The overhead of gathering that data is very low compared to the system itself, and they can sometimes be very effective at narrowing down big problems, seeing which system or what component has got the problem in question. But the problem is when you get a dashboard full of metrics, your performance investigations can sometimes turn into an Hercule Poirot-style murder mystery, right? Which sounds more fun than it actually is. What I mean by that is, at the end of those books, he goes around and says, you're the person who did the murder, you're the person who did the murder, you're the person who did the murder, it's this person over here. It's always the last one they come to, right? That can often be the case when trying to just use metrics on their own to diagnose performance problems. You tend to look around between different metrics, different systems, and without a clear-cut methodology for narrowing down what's going on and pinpointing problems, it can be very hard to jump from that to a specific cause. Another technique that people use for measuring what's going on in their production system is logging, right? Logging is often used for debugging and diagnostics, but it can also tell you a lot about what's going on during a performance outage. So by logging, I mean you're recording an arbitrary event that's being produced by the system that you're monitoring. That could be manual logging, such as log4j, pardon me, or logback or things like that. Systems like that have the downside of being very manual. They tend to have very high overhead. A lot of them are text-based and hard to analyze after the fact. You have to do a lot of work yourself in order to reconstruct things in pure logs, but they can be useful. Logs specifically of components within the system, like logs of GC events particularly, can be a wealth of insight, but that is really only for specific subsystems and components there, like a garbage collector. Another approach that people often use for measuring what's going on in their system, especially application performance monitoring tools, for example, use this a lot, is what I call coarse-grained instrumentation. So coarse-grained instrumentation is when you take a block of code and you add instrumenting code. So you measure the time at the start of an operation, you measure the time at the end of an operation, you subtract one from the other, you find out how long it worked, how long it took, and then you keep track of those metrics. So, for example, a lot of APM tools are quite good at telling you how much time was spent inside, say, the controller layer of your web application, or how much time was spent performing certain types of SQL queries. This is better than looking at metrics on its own in the sense it's a lot more detailed, and as a result, it's a lot more actionable, right? It tells you more specific things that you can then go and look at. But coarse-grained instrumentation does have a downside in and of itself. And that downside is that the more instrumentation code you add to your production system, the slower that system becomes, okay? And also, the more bias you add to that system with the added instrumentation code. So there's always a trade-off between having lightweight enough instrumentation that you can understand what the production system is doing and having detailed and actionable enough insights for that instrumentation code that you can see what's going on as well. On the upside, a lot of APM tools, for example, will automate this process for you, so that's great. Works out the box and gives you some valuable insights out the box. Profiling is a different approach, okay? So as opposed to having specific things that you've thought about ahead of time that you've instrumented, profiling can tell you things which are a hypothesis-free way of measuring what's going on. So profiling might tell you, what methods are using up CPU time, what lines of code's allocating the most objects. You could even find out more esoteric things like where your CPU cache miss is coming from and stuff like that. Profiling is automatic in the sense that once you can profile a JVM application, you can do it for any JVM application, so there's no specific work on your behalf to instrument your code or add some hooks to work with this kind of thing. Profiling can be made to be cheap. It can be made to be very low overhead, so I mean 1% or less, and there are systems that will let you do that. But it often isn't. Traditional JVisual VM-based profiling can add a huge amount of overhead. We'll have a look at how profiling works a little bit later on in the talk. Instrumentation not only can add a lot of overhead to your system, but also it's got a big downside in the sense that it can be blind to certain types of problems. Whenever you're somebody who's writing an instrumentation inside your system, you are not going to necessarily, you'll find it very hard to find the unknown unknowns in that system, because you need to know what part of that system to instrument in order to measure the time ahead of time. So let me give you an example of a customer of ours who was using another APM tool that was instrumentation-based and how it missed a performance problem they had. So they had a problem that they had an HTTP endpoint in their system, and every 5 seconds, it would be really slow. Like every 5 seconds, it would take 2 seconds to respond to any HTTP request, basically. And it would be fine other than that, but it was happening every 5 seconds. That's really annoying for their customers, right? Someone tries to use this thing, and periodically it'll be really slow. What's going on? Nothing to do with the payload or anything like that. They looked at their existing APM tool, which was instrumentation-based, and it had instrumented the servlet request handler in their system. They weren't using raw servlets. It's like the 2020, right? But they were using something that under the hood boiled down to using servlets. And that system, it didn't even show the pause in terms of their application. So what was actually going on here, the kind of more root cause, was that Tomcat had a resource cache for a bunch of different resources. And it expired this cache every 5 seconds. And one of the resources on their application had an ingenious, we'll try and do your work for you, automated class path scanning mechanism that would just go and block the whole reload for 2 seconds and slow everything down. So the thing that caused HTTP requests to be really slow was not actually a part of the HTTP request processing mechanism. So anything that instrumented that would just miss it completely. Whereas a profiling approach that's more hypothesis-free, that's just looking for where your system is spending CPU time, found this problem almost instantly. And yeah, this is an idea when I talk about why you want to be careful about instrumentation being slow. Whenever you're trying to solve performance problems, you want to make sure the tools that you're using aren't also the cause of a lot of performance problems. I've hit a number of people who've had this kind of issue where they've rolled out new versions of some of these tools and they have had significant overhead and had significant slowdown of their systems as a result. You want to be the solution, not the problem. Okay, so surely there's a better way. We said metrics were quite useful. They were cheap, very insightful sometimes, but they weren't necessarily actionable insights. They didn't tell you where in your code base you went to fix problems. So how can we think about using profiling in a production setting in order to provide that insight rather than relying on instrumentation-based approaches to tie back what's going on under the hood? And that is where continuous profiling comes into play. So continuous profiling, how would we use that in our system? Well, you want to be thinking about what in your system has got some particular problem, and looking at the particular time period of machines that you want to profile or applications. Look at a particular type of time to profile or type of thing to profile. We'll talk about Wallclock versus time versus CPU time in a second. You could also be doing memory profiling as well. And also, then you want to have a look at the results of that profiling to tell you what the dominant consumer of the resource is. So the dominant consumer here is the thing that's causing your main bottleneck, the thing that's the really big problem. And then fix that biggest bottleneck, iterate and repeat. I say here, fix the biggest bottleneck, redeploy, iterate and repeat, because often removing the biggest bottleneck can change the way profiles work. It can make things shift around in your application, and it might not be that the second biggest bottleneck is still the second biggest once you've removed the biggest bottleneck. So I've used this kind of concept of CPU time versus Wallclock time. What do we mean by that? Well, I like to think of this in terms of a coffee-based analogy. That's completely unrelated to my addiction to coffee. The CPU time is the time where you spend actually on CPU, running code, retiring instructions. Whereas Wallclock time is the time you spend from the kind of beginning to the end of the operation in question. So if you've got a coffee shop like this, and the Wallclock time equivalent there might be from the beginning of entering the queue to the end getting your coffee, whereas the CPU time might be the time spent just brewing the coffee itself or taking payments, the time we're actually sitting there rather than the kind of queuing time, waiting time. Now, you need to understand, if you're looking at profiling a real production system and you want to be able to spot all sorts of different problems there, you need to be able to measure and understand both CPU time profiles and Wallclock time profiles. CPU time profiles are really, really useful for understanding computationally intensive hotspots in your system, okay? Inefficient algorithms, often also things like code that shouldn't be executing but actually is. You would be shocked at the number of times that I have seen profiles of people's production systems. And you know what the number one bottleneck is? It's filling in the stack trace on an exception. And then you ask them, why is your system spending all its time throwing exceptions and catching exceptions? And they'll say, I didn't know it was throwing exceptions and catching exceptions. And they'll realize that there's some sort of very, very strange behavior that had two bugs making it work. It does happen quite a lot. But CPU time profiling, very useful for understanding those computational hotspots. Also very useful for understanding time in terms of what is actually running on the system. Wallclock time profiling, however, is very useful for diagnosing when you're not bottlenecked on CPU. So, for example, blocking systems that stop CPU usage. Now, blocking might be, say, a lock contention problem, where you've got a bunch of different threads updating a shared data structure, and you have a lock protecting that data structure, and they're all sitting around there waiting on that lock. Now, in practice, a lot of those lock contention problems are not necessarily in developers' code, because not that many people use locks that extensively in their code base, but it may well be in a library that you're using under the hood that you can see where that bottleneck is. It can also be very, very commonly that you are waiting for an external operation to return. So some kind of I/O. If you're doing microservices, who's got a big microservices e-deployment here in the room? Not that many. Wow. Is that microservices have peaked and gone down, or you guys aren't jumping on the bandwagon yet? Who knows? Okay. So, for example, in those kind of situations, you might often spend a lot of time making HTTP requests to other services in your system, and Wallclock time will help you see when your CPU is sitting around waiting for those requests to end, when you're blocked on that external service. Okay? Profilers provide a bunch of different views to visualize the data they gather. So, the most simple view that anyone has in a profile is just a regular hotspots view in a profile. So that's a series of methods within your application, the amount of time that gets spent within those methods, and perhaps a visualization at the time, like a graph, or sometimes the number of calls that have been made with those different methods. Some profilers let you see the line number information within that hotspot, and some profilers also tell you things like what were the stack traces that caused you to actually get to that hotspot as well. A more modern visualization that people like is flame graphs. Who's used flame graphs? A few people? Cool. So flame graphs are a way of visualizing the time usage within your application in a way that's very context sensitive. So it shows you also what bits of your application were calling or invoking other bits of your application when that bottleneck happened, or when at the snapshot that you're looking at. So each box in a flame graph corresponds to a method within your system. And you get flame graphs going one way or the other. Most of them go bottom up. This graph comes top down, which some people call icicles view. But yeah, this is a top-down flame graph. And in the top-down view, each method in this graph is calling the box below it. Those are its children that it's calling within its application program. So you'll see in most Java flame graphs, the top method is like javalang thread.run, okay? Because that's what ends up calling the other methods in your application. As flame graphs, the width of the flame graph of each box is the time spent within that method and all of its children. So you can see, for example, this method here is very wide and only has one child, and that one child is very narrow. And when you see that narrowing in process within the flame graph, that's when you get a lot of self-time, when those flame graphs narrow down. And those are often the methods that you should draw your eye to when seeing flame graphs, because they're often the things that tend to be the bottlenecks in time. Very, very concise way of displaying a lot of data quite quickly. So flame graphs, fantastic visualization tool. And then there's the way that we implement profilers under the hood. So I mention this because often people have tried doing some profiling on a production system. They've hooked up a profiler. It's slowed the system down massively. They don't want to run that on all the time. And they want to ask you, well, how are you going to do this always on in production? That's a terrible idea. And the answer is you just have to implement your profiler in a way that's very lightweight and efficient and can be run all the time. The first generation of profilers that were written were instrumenting profilers. So they had that same instrumentation approach. Every method in your application, they'll take the start time, they'll take the end time. This is inaccurate. It modifies the behavior of the program. Why does it modify the behavior of the program? Well, that calculation of the time is fixed on a per method basis. Okay? Calculating the time at the beginning and end of the method. And if your method is really cheap, like a getter or a setter, for example, then that overhead of calculating the time actually dominates the work done in the method. And for methods that are really, really big and take a long time period to run, that time is still the same fixed amount of time, but it's a much smaller proportion. So what instrumenting profiles actually result in is smaller methods being overstated, or I shouldn't say not smaller in terms of lines of code, but quicker methods being overstated in your profiles, and slower methods that take more time being understated in your profile. So they have a measurement bias and inaccuracy. And they are very, very high overhead. The best instrumenting profilers tend to be about 2 times slower than what your system would run without any profiling. So a lot of people use sampling or statistical profilers. Everyone loves statistics. The way sampling and statistical profilers work is they periodically interrupt your application, very, very briefly in an ideal case. They look at what the stack is executing at a certain point in time. So in this visualization here, each green line is a point where we've interrupted the stack to collect what's going on, and we've measured some Java methods which are being run at that point in time. And then you can build up a picture from those samples of the stack traces of which method is calling what and what time is being taken up on a probabilistic, a statistical basis. Okay? So far, so good. But unfortunately, it's quite hard to accurately sample your actual application. So who here is familiar with the concept of a Safepoint? Okay, good. New for a lot of people, that's excellent to hear. So Safepoints are a mechanism inside the JVM for bringing Java application threads to a halt, for interrupting them and stopping them. They're most commonly used for garbage collection, but they can also be used for other things within the JVM, replacing code and also fattening and thinning locks as well. Now, the way Safepoints work under the hood is that there is a periodic Safepoint poll to a known memory location. Okay, so it's just a read of a specific point of memory. And the idea that this Safepoint poll is really, really cheap in terms of your application, because that page that it's polling to read is always sitting in your CPU cache. And then when, in your application, you want to cause a Safepoint, you want to bring all these application threads to a halt in order to do something like run a garbage collector, then you just take the page that you're reading, or that the Safepoint poll reads, and add a handler for any read, so you protect that page, and then that interrupt handler will be executed, and its code run, and then you can kind of bootstrap your way into JVM code. It's a clever mechanism, it's very cheap, but the thing about what happens with the Safepoint is that it's a global operation, so it's a global pause. There's an introduction of a non-global Safepoint in Java 11 or later, but most people are not on that. And it also introduces a bias because of where those Safepoints are located. So remember I said that there was a poll. There ends up being a poll for these Safepoints at the beginning and end of every method, and also on the back edge of most Java loops. Okay? So as opposed to your periodic sampling of a stack trace being nicely distributed at times that you think it is within your application, actually it only happens at points where Safepoints happen. And that results in a little bit of bias. All of those, so the Safepoint bias here is showing that all of those light green lines are actually Safepoint polled and actually measured where the red line is. Gets worse. One of the JVM's most effective optimizations, and something it's known to be really good at, is inlining of different methods. And inlining removes Safepoint polls. It's one of the reasons why inlining reduces the cost of a method call itself, is removing that Safepoint poll. And so if you, for example, imagine that all those purple methods in this very hypothetical application got inlined into their callees, then any Safepoint polls would get aggregated elsewhere. So as opposed to you polling the application here, and here, and here, and here, you just have one poll at the end of that bigger method that these little methods have been inlined into. And that can skew the results of sampling profilers quite a bit. It also gets worse because, remember I said that those long loops also have Safepoint polls on their back edge, so that's when your application goes from the end of the loop back to the start again. Hotspot will remove and optimize away Safepoint polls for what it considers to be counted loops. So that's loops that kind of very informally look of the form like for int I equals 0, I less than n, I plus plus, that kind of loop structure. So that can also skew your Safepoint polling to exclude data points within that loop, which again makes the data less accurate. And then we talk about time to Safepoint. Okay? So when a Safepoint happens, it's a global Safepoint. You need to stop all of your threads in your application. Okay? And if you have any individual thread that is doing an operation that is not being Safepointed, so for example, maybe a mathematical computation with one of those tight loops that runs for a while, you can get longer time to Safepoint pauses as these other threads have finished, Safepointed, and they're just waiting for this one thread to reach its Safepoint poll so they can all come to a halt for the VM operation to kick off. And that means that your application is sitting there, paused, not doing work, so there's an overhead to this mechanism as well. Not necessarily a huge one, but if you want to be doing it all the time, it's a big problem. So how does that affect sampling profilers in Java? Well, the regular JVM-TI approach for implementing sampling profilers in Java is using get all stack traces in the JVM-TI API. It's very expensive if you do it frequently, and it can be inaccurate, because it only tells, it brings all these threads to a safe point in order to capture the stack traces. Now, that means all of the biases that we've seen just now around safe points, it's exposed to, and it has high overhead, and it's pausing your threads when you want your threads to be off there doing work. So, how can you implement better profiling in Java? Well, there are two things you need to do in order to profile. First, you need to interrupt the application so you can capture a stack trace. Then you need to sample, I say the resource of interest, I mean a stack trace in method profiling or the allocation point in memory profiling. Now, advanced statistical profiling in Java, which you can do today with reliable tooling, is using operating system signals to generate those interrupts. So most operating systems, most modern operating systems, will implement a type of signal handler that will let you periodically send an operating system to a process. So most people are very familiar with, like, for example, sigkill and sigterm, right, for shutting down Java applications, where you send it a signal, an operating system signal that means either stop politely or just stop what you're doing right now, sir. Whereas sigprof can be another signal handler that you can register a callback for that will periodically be run on threads randomly throughout the process. It's very lightweight, it's very cheap, it's run by the operating system, it's the fastest way to interrupt a process. And it allows you to sampling the resource of interest. Well, there's a few different ways of doing it. There's an API within the JVM called async get call trace, which will allow you to capture the stack trace at points of interest that you can run inside a signal handler. Signal handlers are quite tricky to implement, so you can't necessarily just use regular Java JVM TI methods whilst a signal handler is being run. You can't call malloc, for example, in a signal handler. That's an example of how fiddly they are to write. You can examine JVM internals for other resources, so you can look at what state the thread is and things like that if you want to return that kind of information to your users, which we do, for example. Very useful. So it's not necessarily used by all profilers. I know there's a new version of JVisual VM that can use flight recorder that will work this way, but traditional Visual VM does not tend to work this way. Traditional desktop commercial profilers don't tend to use this kind of method, and as a result, I mean, if you're running this in a desktop environment, the overheads aren't so bad, but if you want to run this in a continuous production environment, being very, very low overhead, as I've said, is critical, so you need to be using this kind of method. There are some low overhead open source profilers. So async profiler, flight recorder is now open source, so that's another tool you can use. Things like Solaris Studio. There's also perf and the perf mapper agent that use a different stack trace capture method, but a similar signals-based interrupt approach. I call those ad-hoc production profilers because they're all very good at gathering the data, so they're low enough overhead to be used in a production system, but they don't have sort of the continuous profiler aggregation concept, which we'll talk about in a sec. In practice, people aren't just put off profiling their production system by the overhead and the technical issues. There's a lot of practical, personal issues that well, not personal, but people issues that you might hit as well. So firstly, if you've got a production system that is undergoing some kind of partial outage or performance degradation, people do not like connecting up some ad hoc open source tool to see what the heck is going on. You may not have production access. So who here can SSH into their production servers? Some people. Ooh, about half the room. Cool. Some people are not allowed to SSH into their production servers, for example, like Chinese walls inside banks, things like that. It's a manual process. It's hard to automate. And also, it doesn't really scale out to a very cloudy environment, the idea of going in and SSHing into these few servers to look at that kind of data. So there's a lot of barriers to ad hoc production profiling, and in practice, people don't do it very much. Okay? But what other benefits do we also get if we just profile our production system all the time? Firstly, we get historical data. So when you look at a profile of your application for the first time, it can be doing things that are a bit weird or unexpected. As I mentioned, a lot of people throw exceptions and catch them, which they didn't notice. But if you have historical data, that also allows you to compare with historical scenarios and see what the difference is. It's possible to diff profiling views as well and see what what's got slower or faster between those data points. Historical data also allows for post hoc incident analysis. So what do I mean by that? I mean, suppose something was slow at midnight and you had users in a different time zone, and you woke up the next day at 9 a.m. and you wanted to see what caused that slowdown around midnight. You can't go back in time and then SSH into a system and look at what was going on. And if you can, please come and tell me after the talk how your time machine works. Historical data that's always gathering that data and you can look at and query retroactively means you can look at those things if you've missed them, or if, for example, they were intermittent one-off things, like, say, a login page was slow or one resource endpoint was slow, and you didn't have many samples of it being slow, but if you profiled for a month, you could see what was going on over those different samples. It allows you to put those samples in context as well. What was going on there? Was it a machine type on AWS that this was slow on? Was it a particular CPU? Was it a location? Was it just one machine that has some faulty piece of hardware? Was it that you've got different application versions? You can see that context from that querying that historical data. Ad hoc profiling is not so strong on that kind of thing. This kind of continuous profiling approach isn't completely new as a concept. Google published a paper a number of years ago now called Google-wide profiling, which I put the link there. I'll throw the slides up and mention them on Twitter afterwards. They profile a lot of their services internally for a number of years, and have a similar kind of historical data querying and analysis system that you can look at after the fact. Very useful for engineers investigating problems. So, if we're doing production profiling, continuous profiling, I think we not only need to think about using JVM agents themselves, but also some kind of aggregation service that keeps track of lots of those different agents and keeps track of that data, allows you to do historical querying, and allows you to see reports of that historical querying. That's the kind of service that we offer at Opsian. So, in summary, it's possible to profile in production with very low overhead. You just need to use that kind of advanced statistical profiling technique I talked about. If you overcome those practical issues, you can just profile all the time. It gives you great data, and we gain new capabilities by doing that. Let's look at a more broader summary of the talk as a whole. So firstly, big thanks to a bunch of different people here. So Brendan Gregg was the guy who kind of came up with flame graphs as a visualization, and there's people like Andre Pangin, Jeremy Manson, Nitzen, who did lots of work on some of the open source tools for low overhead efficient profiling, and also, for example, the flight recorder and mission control teams who have a similar kind of very low overhead measurement technique. But yeah, in this talk we said performance matters for you, and finding those unknown unknowns can be very helpful. Development and production are different environments. It's hard to solve production problems in a development environment. Metrics can be unactionable. You can't just look at a metric and see exactly which line of code you want to fix. Instrumentation can have, a priori understanding issues and high overhead. Continuous profiling is really, really useful for filling in the gaps and helping you see what your system is really doing, not what we think it's doing. I think we need a bit of an attitude shift on profiling and monitoring in general. And that sort of means doing kind of three different ways. Firstly, thinking about this in a systematic, not ad hoc approach. So always having methodology, tools, approaches in place that let us understand what our actual production system is doing. Not only worry about these kind of problems when something goes wrong and when you're under the stress of an incident or an outage or a high-pressure system where you might make emotional, reactive decisions. And also being proactive and not reactive. So putting in place, again, partly that's setting up instrumentation and things, but also partly about thinking what kind of tools and approaches can help us diagnose these problems. And continuous profiling, being always on, having a normal part of your business process to be measuring these things is super critical to achieving that. In short, please do continuous profiling in production all the time. Obviously, You know, I run a company. I'd love it if you use our tool, but what I really want you to do is do it as a methodology, do it as an approach. You'll find it really, really useful. And that is the end of the talk. I hope you all enjoyed it. Thank you very much. And if you have any questions, you can ask them now.
How does these tools work with all the asynchronous libraries we have these days? Because I've used profilers.
Yeah.
And usually the output with async systems like that.
Yeah. So I think there's a few different things there. Is the output garbage for async systems? And the answer is it can well be, yeah. But firstly, the biggest problems that I've hit with async systems have often been when they've not been async. When you have an event loop that looks like it's async and has actually got a big blocking JDBC call in there that's sitting there taking ages, right? They will tell you about those problems anyway, at least in a Wallclock time view. Secondly, CPU time profiling still works for async systems in the sense of telling you what the hotspots, what the hot methods are in terms of CPU time, and it will also in practice tell you a lot about what code is running there. The context can be a bit challenging because it's often an event that's triggered something, but that is still a useful insight to get. Thirdly, I'm hopeful that with Project Loom coming along and fibers as a concept coming as a proper primitive to the JVM, it'll be easier for us to write async code that has that stack trace context and that we can read out there as well. So I think the long-term full solution of those things is kind of Project Loom. But at the moment, it's still, I don't know, it's an imperfect situation at least. Yeah. Any other questions? No? Shout if I'm missing you. Okay, thank you very much. Hope you enjoyed the talk. You can always